Okay, so I now want to upgrade our source. Okay, so right now, x and y are the destination points at which we are evaluating the source. Okay, so those are the arguments coming into the source, and m is the strength of the source, the strength of the source or sink. I simply would like to add two more parameters, x0 and y0, to tell the source where I want to locate it. And then I can simply do this arctan, change it to y minus y0 and x minus x0. Okay? Okay, so let's run this again. And we're going to come down here. Now this was our original one at 0, 0, right? So I'm going to upgrade this and say x0 equals 0, keep it here, and y0 equals 0.0. So if I run this, it should stay the same. Now let's say I want to move the source to +1. So all I have to do now is go and say x0 equal 1, and it stays at y0 equals 0. Okay, right? Makes sense. Let's say I want to move it to 0.5, 0.5, 0.5, 0.5, and run it. Okay, put it at 0.5, 0.5. Okay, that's great. Okay, so now I would like to put a source and a sink behind the source. So I'm going to keep the source at 0. I'm going to do a sink. M is minus 10, same strength of the sink, of the source. And C3 is the strength of the sink, is the stream function of the sink. I'm going to call it source. X, Y, remember, are the global coordinates of your grid, of your computational domain. And I'm going to keep it, do this M again. But then now x0 is equal to, let's put it at 1.0, and y0 is equal to 0.0. Now let's upgrade C total to add the sink. Okay. So now we have a source at 1, 0, and a sink at, sorry, a source at 0, 0, and a sink at 1, 0. Yeah.
Never mind, I see that. Mass flow.
Okay. Are we synced?
Can you go back up to the source definition?
See how simple this is? And this is, I'm making my math, my implementation be expressive. The same way, because my stream function is always m over 2 pi theta. But theta is something different when I move the source around, or the sink. Okay? Are we good? Are we ready to execute? Okay. Oh, look at that. That's cool, right? So now we have a source and a sink. Okay. Now you can play around with the strength of the sink, maybe make it of a different strength, right? So you're going to get different profiles, right? When you get, see, it's, now you got a very strong source and a very weak sink. Only some of the streamlines go into the sink, but the rest, they flow over it, right? So you can adjust that strength to make all sorts of shapes. And that is problem 3 in your assignment. We're going to put a bunch of sources and sinks and adjust their strength to create a certain shape. Okay? And we figured out that condition in the assignment. Okay? Okay. That's cool. Right? See? Yeah, like, you know, it's a different, it's going to give you all sorts of shapes. Now, when you do this, if you, let me move this a little bit farther, like 1.5, and do the same strength for the source and sink. This is called a Rankine oval. Okay? It might look like a cylinder to you, but it's just an illusion because this is not, the aspect ratio is not correct on this plot. Okay? The aspect ratio is not correct on this plot. So if I want to do a correct aspect ratio, you have to create a figure. Okay, I'm not going to do that now. I don't want to overwhelm you with that stuff. But okay. So now, what happens? What do you think would happen if we start if we start bringing those, let's actually do a figure. plt.figure, okay, fig size equal 4 by 3. Or 3 by 2, sorry. Let's do it 3, or what is it, minus 2? So 5 by 2. Oops, 5 by 2. Okay, now that's to scale. That's the correct aspect ratio. Okay, that's the correct aspect ratio. Let's see, maybe 7.5 and 3. Okay, a little bit better. Okay, so now what would happen if I start bringing the source and the sink together? What will happen? Give me a guess. Yeah.
Create a sphere.
Okay. So Brandon said they create a sphere
Or not a sphere.
or a cylinder. Okay.
And I think if they're right
Yeah.
if they're right on the top of each other and they're equal strength, then it would. If they're linear, they'll just cancel each other out.
Okay. So we have two different views. One thought is that if they're the same strength, they're going to cancel each other out because they're linear. And Brandon's saying they're going to turn into a cylinder.
What was
I
it?
mean, if they're on top of each other?
Hmm. Yeah, I'm bringing them on top of each other.
Yeah.
Even you get them close.
I'll stick to my answer.
Okay. Well, both of you are right. Because if you keep the strength equal, they're going to cancel each other. Whatever's coming out is leaving, right? So nothing, there's no net flow. But if the strengths are not equal to each other, something else will happen. Okay? So let's first just kind of observe this a little bit. Okay, so the source is at x0 equals 0. Let's start moving the sink towards the source. Let's do it at 0.5. Okay, they're still the same strength. Okay, this looks like a circle. Okay, still looks like a circle, but okay, let's get them closer. 0.15, 0.05. Starting to disappear, right? 0.005. Look at that. And then 0. They canceled each other out. Indeed. Because they are the same strength, they're going to cancel each other out. Okay? So, that's not a very interesting case. But the interesting case is, although like a source and sink can be made to look like a cylinder, like a circular shape, it's quite complicated to determine the size of that cylinder. It's not kind of that straightforward. I mean, you can do it by putting them. You have to figure out how far apart from each other. And from a practical standpoint, let's say you want to do flow over 35 cylinders. You're going to have to figure out the spacing between the source and sink. Just try for each pair of source and sink. It's kind of annoying, pain in the neck, right? So it would be really cool if we bring that source and sink together, but also change the flow rate in a way that they don't cancel each other out. Okay? That they don't cancel each other out. So let's do the math first. Let's do the math first and see how we can do that to create some interesting shape. Okay. So now I'm going to define this A quantity. I'm going to say A is equal to 0.5. So one of them is at x minus 0.5, and the other one is at x plus 0.5, right? And the strength is still at 10. I'm going to start at 10. Okay. And so x0 for the source is going to be at minus A. And the sink is going to be at plus A. Okay? I haven't done anything here except that I put them separated by the distance A. Now I'm going to shrink A, but I'm also going to change the strength inversely proportional to A. If we didn't scale it by A, as we demonstrated earlier, then they will start canceling each other out. Okay, what's the next number? Let's do 0.1. Okay, now they're getting closer and closer to each other. 0.01. Look at that, right? They're turning into a circle. Let's do 50 levels. And so they're turning into actually what we call a doublet. Okay, I'm going to keep bringing them closer to each other. Look at that. So you're starting to recover the flow over a cylinder. Okay, and no matter how small you make A, it will settle to this shape. This is called a doublet. Okay, and it has its own quantity. So we don't have to put a source and a sink and do all of that anymore. All we have to do is implement that formula, minus k over pi sine theta over r, and we will be good to go. Okay? So let's go ahead and do that. Yeah, k is, remember I said I want to scale m as inverse as 1 over a, or you could put it k over a, some other fixed value. Okay, as long as it changes as it grows as 1 over a. Okay. All right, so let's program the doublet now. And same thing. So I'm gonna actually just copy the source, put it here. So notice how we grew from a simple uniform source at the origin. We moved the source away from the origin. Now we're going to do a doublet, also not necessarily at the origin, at any location, at any possible location. So I'm going to call this a doublet. I'm going to give it the symbol K to be clear. Okay. And for the doublet, we had a sine theta over r. So I still need this theta, but I also need to compute r. And r is simply the square root of x squared minus y plus y squared, or x minus x0 squared and y minus y0 squared, because we're located, everything is in reference to the doublet. Okay? So mp dot square root of x minus x0 squared plus y minus y0 squared. Okay? Now my psi is simply minus k. Okay. I'm going to absorb the pi into k. You can still divide by pi, doesn't matter. Times mp dot sine theta over r. Okay. But there's a singularity at r equals 0. Okay. Go see a psychologist. I don't know what to tell you. Don't evaluate it at the singularity. Or add a little small number over here, r plus 10 to the minus 10. So you don't get that warning. Worst thing it's going to do with Python, which is great, is just going to throw a warning and move on with life. You know, it's not like you're installing something on Windows. You used to install something like, I cannot install this software. Like, try. You know, well, the libraries are incompatible. Just try, man. Just try. And you can't install it. So Python is nice because it allows you to just install things, to just run things. Okay, I'm gonna try to see if I can make this error show up at r equals 0. So let me see. Excel. Okay. I'm gonna do. Okay, anyway, if you get this warning, just add, either neglect it or add a little small number to your denominator. Okay? Oh, look at that. Very nice numbers. Okay. Okay, so I want, the reason I I change the number of points is because I want Python to go and evaluate at r equals 0. Okay, so that it gives me that warning. Okay, let me show you. So now we have a doublet. We don't need sink and source together anymore. I'm gonna kill all of those, and I'm gonna make this a text. So uniform flow plus doublet. Okay, so let's copy this stuff over here. Uniform flow, and I just copy everything. Okay, uniform flow, we still have that, and then we're going to do a doublet, and I'm going to call this k is equal 1, C2 is a doublet at x0 equals 0 and y0 equals 0 with a strength k. Okay. C total, C1 plus C2. Well, doublet is not defined because we're going to execute this cell. Okay. And let's also copy this guy. Oh, look at that. Invalid value encountered at divide. Meh. Whatever. I don't care about you. Like, yeah, invalid value encountered in divide. Yay. So it's a nan. So what? It still computes. If it bothers you, go add a small number here. If you're not happy with it, just go divide by r plus like 1e to the minus 10.
You can also disable warnings, and then you want to
But I like warnings because sometimes I might commit a grave error, right? Okay, now you don't see that warning and you're good. Okay?
You're not allowed to be put on any Mars rover.
Now this doublet, okay, mimics the flow over a cylinder. Okay? You want to see some nicer contour lines, some nicer levels. You could do a lint space over here between like minus 10 and 10 and do like 30 contours, and you get some nicer contours. Okay. And you can also plot a specific contour. So let's say I want to look at, so my guess, my intuition tells me is that this flow is so symmetric, contour lines negative below, positive above. I bet you that the streamline value that has c equals 0 is right on that cylinder. Okay, so let's test that hypothesis. So you can also plot a single contour x, y, c total, and levels equal 0. Okay, that's the contour line of c equals 0. It's right on that doublet, which looks like a cylinder because every streamline, like we said,
The inside ones have c equal to 0?
no, there's a bunch of contours inside it, but we don't care about those, right? Again, potential flow is very visual. You can choose any streamline and say this is my wall. In this case, the doublet, because there's like one nice streamline around it, like if we forget about these streamlines over here, don't do anything here. Don't care about what's inside. I don't care about the origin. There's streamlines inside of it. I don't care about that. Because the flow is going to come and go over here. It's going to do something inside, but it doesn't matter. I choose this streamline to represent my cylinder. And with this, you can get flow over a cylinder. That was one of the first problems in your first homework assignments. You had that that pressure distribution and whatever. This is how you do it. Now, you have an analytical formula for uniform flow over a cylinder. With Bernoulli, you can get the pressure distribution everywhere. I don't care about what's inside this circle, but above it or right at it, I have P. I have all the values of P, and then you can compute lift and drag, which are going to be 0, because potential flow, right? And do all sorts of other things. Get the velocity profile, and share it with the world, and be happy. Okay? But that's the usefulness of this doublet. Okay? In the homework assignment, where you're going to use a bunch of doublets back to back to mimic the flow over an airfoil. So if I were to place a doublet just behind this, just for the sake of just playing around with this. So let's place another doublet, k equals 0.5, let's say, and do C3. Okay, and we're going to place it at 0.3, let's say, and plus. Same effect that we had with the, okay, now look at that. It's looking like the beginning of an airfoil. Now, if you place another one here, it's going to keep extending that line. You're going to get some kind of airfoil. Now, I'm just kind of guessing these numbers over here. You're going to have to solve a system of equations to obtain these strength and kind of do this, for example. Okay, now you have another kind of weird shape, like a flow over a, I don't know, pumpkin squash or whatever, right? Right? But kind of that's the idea. That's the concept of panel methods or line vortex methods, etc. The problem with all of these is that they do not generate lift or do not generate drag. So you cannot use them to compute lift on airfoils. And so you have to do something a little bit different to mimic the illusion of lift. And that is to add what we call an irrotational vortex. Okay. What is an irrotational vortex? It's a vortex that is irrotational. That was a very mathematical statement there. Sounds like a mathematician, right? What is infinity? It's an infinite number. Okay, if you want to stick around for a minute, define vortex, xy, strength of the vortex, x0, y0. And I'm going to copy theta and r, mc, return psi. Okay. Okay, psi is minus k times np dot log of r, right? I didn't even need to compute theta over here. Okay? All right, so now I'm going to go back to this doublet flow. I'm going to erase these guys. I'm going to do C3 is equal to vortex. Okay, vortex at the entire plane. Okay, and then let's do k is equal minus 1, and then at x0 equals 0 and y0 equals 0. Okay, so let's see what happens. Notice how the streamlines now are lifted up. See how that streamline now is lifted upward. Now, if you go ahead and analytically or numerically compute the pressure, the lift based on the pressure distribution on this, it will be non-zero. And it will be directly related to the strength of the vortex that we added. Okay? Without the vortex, I'm going to remove the vortex. Okay, let me, easy way. Okay? I'm going to call it gamma for the strengths of the vortex. Okay? K is equal to minus or plus gamma. So no vortex here. Nice uniform flow. There's not going to be any lift or drag here. Okay, let me also eliminate this for ease of viewing. Now, when I add the non-zero vortex, so minus 1, then you see the streamlines are shifted either up and down, okay, depending on the rotation, because plus value for the vortex, either rotating like this or like this, is going to generate lift. It's like when you have, I don't know if you've seen these old vessels with a cylinder spinning in the middle in water. So if you spin the cylinder, the ship will move, right? Because it generates lift when you spin a cylinder. So this is the same effect. You have a cylinder that's spinning is going to create lift. And that's the only mechanism. Have you ever seen those, like very, very old ships before before having like these propeller ships? They would have a cylinder in the middle that would spin, and then the ship would move forward because it would generate lift on the entire ship. So that's the same thing. It's moving. It's as if the cylinder is moving in this direction. So it's spinning, and it's going to move in this direction or that direction, okay? Depending on the value of that gamma. Gamma is positive or negative. Okay. Same thing, right? It's the streamlines are shifted upward or downward. Okay? Let me see if I can. Yep. This is, it's called a rotor sail ship. Window, move. See, they have these huge cylinders that spin. And they could make the ship kind of move in all sorts of different directions by adjusting kind of the spinning strength. And this magnificent example, Flettner rotor, whatever. Rotor sails in action. Is that a movie? Oh yeah, look at that.
I have the ability to help people escape reality.
Sorry. See how they're spinning? And the ship is moving.